Okay, continuing with our discussion of the IEA report on AI and energy, let's look at the chapters. We looked at the uh, executive summary, which gave most of the most salient points already, and we'll read these anyway because there are some additional points that we must understand and look at. So, the rise of AI and its nexus with energy, it's a new paradigm that's emerging. Artificial intelligence is emerging as one of the most consequential technologies of the 21st century, and the state of the art AI model has grown some 35,000 times since 2014 if you look at the amount of computation used, and they are capable of many things. So deep fakes, so generate text, videos, audios, predict complex systems like weather, makes robots smarter, more flexible. We already looked at many of these things in other podcasts in more detail. As models have become much more capable, AI has become an industry with billions of dollars of annual investments and trillions of dollars of financial market value at stake. So the large companies' AI adoption rates rose from slightly over 15% of the firms using AI in 2020 to nearly 40% in 2024. So the uptake is going fast, and it will grow even more faster. However, smaller firms use AI much less, with missing expertise appearing to be a key constraint. We will look at that a little bit, but even at households, AI is highly globalized, and it's there in even the developing countries like Brazil, India, Indonesia, and US reports regularly the using of generative AI along with these other countries. In the US, it may not be so surprising, but for other countries to catch up so fast just tells you that AI may be much more democratic in its access and growth than the other technologies, but also that the economic interests of companies that are making and selling, and often they are inbuilt with phones and cars and appliances you buy, so it's not necessarily a separate entity. AI is a product of extremely complex supply chains. The machine tools used to make high-end chips are among the most complex machines in existence today, and their production is dominated by Europe. Chip production now is a key issue with all the global conflicts going on, and with the rare earth minerals and so on needed to produce them, and the technology and expertise. Chip production is concentrated in East Asia, with the largest company holding a 65% share. The US dominates AI model development and deployment, although China has also made strides recently. So if somebody is sitting in East Asia and controlling 65% of the share in chip production, then US is trying to ramp up its chip production, but is having some issues. India is trying to get into the game, but is way behind, and so on. The rise of AI has huge implications for energy, of course. We expect that a large data center can consume as much electricity as 100,000 households, as we said. The largest currently under construction could consume as much as 2 million households. So data center energy demand is an issue, but innovation may come from there as well. Hardware and software efficiency, the AI models are improving rapidly, and you can look at some number, but real world implementation may be much more efficient than the numbers you get by looking at idealized cases. But lack of data on the energy consumption of commercial models actually inhibits the assessment. Those are kind of trade secrets, and companies may not want to say how big an energy hog their AI tool or AI software is. This report explores how much energy AI will need, what the uncertainties are in the outlook, and what sources will help meet this demand. It addresses how AI can be applied in the energy sector itself, and how it can contribute to making energy system more secure, affordable, and sustainable. So including itself. So if it is big part of the energy demand, then it will be also making itself more affordable and sustainable. It also explores the broader ramifications for energy security, innovation and investment, and the energy policy landscape. To look at one figure, percentage of large firms reporting not using AI by reason, this is for the European Union, So I'll just read off the items. Missing expertise is the dominant reason that firms do not adopt AI today, followed by privacy and legal concerns. So missing expertise, privacy concerns, legal concerns, missing data, integration challenges, high costs, ethical concerns, and there is even people who believe, corporations, businesses who believe AI is not useful. Okay, jumping ahead to chapter 2, then energy for AI, the evolution of energy demand and how to meet it. Artificial intelligence model training and deployment occur mainly in data centers, because without data you have no AI. AI learns from data, it's physics agnostic, so it doesn't need to know the physics. We build so-called data-driven models, and mechanisms come out of them, patterns, etc. So in total, electricity consumption from data centers is estimated to amount to around 415 terawatt hours, or 1.5% of global electricity consumption in 2024. It has grown at 12% per year over the last 5 years. We looked at these numbers already in the executive summary. So there is a base case projection for data center electricity, and by 2030 it's going to be jumping up. So they have lift-off, high efficiency, and headwind scenarios that capture the uncertainties in efficiency improvements in hardware, software, AI uptake, and energy sector bottlenecks. Okay, in the base case, electricity consumption from data centers rises to around 945 terawatt hours by 2030. US sees by far the largest absolute growth, followed by China and Europe. Data centers will account for less than 10% of the growth in global electricity consumption by 2030, which means it's not going to be as big a impact on climate change, emissions, etc., as we have been talking about, or flags are being raised a lot. The lift-off case assumes stronger AI uptake and limited local constraints on data center build-out. So I didn't say what it was in the first podcast, but here we have some details. In this case, consumption reaches over 1260 terawatt hours by 2030. The high efficiency case is driven by energy savings in both software and hardware. Consumption reaches 800 terawatt hours, so a little bit lower. In the headwind case, it reaches around 670 terawatt hours by 2035. The spread of uncertainty widens further, spanning 700 terawatt hours to 1720 terawatt hours across the 4 cases. The energy demand could be lower because the deployment is lower versus efficiencies. So high efficiency case is that you will deploy but use less energy. Headwinds is the other way. Natural gas generation to meet data center demand increased by around 170 terawatt hours from today's levels to 2035 in the base case, mostly in the US. In the lift-off case, it grows by 290, and so you get the idea. This reflects their broad availability in terms of renewables, short development times, economic competitiveness, and technology sector procurement strategies. Nuclear power also contributes, and as I mentioned before, if these modular reactors come along, then a lot of these big corporations may go on their own to produce nuclear power, hopefully safely. Grid congestion and connection queues are growing in many regions, and supply chains for key components like transformers and gas turbines are stretched already and will be further stretched as the demand grows or outpaces production and grid improvements. So there are some numbers here that I will not read because there are a lot of details that go into the projections that we haven't paid attention to. Avoiding this risk will require a range of actions from both the energy and technology sectors. Permitting times for new projects need to be cut. So that permits time for new projects that maybe need to be cut. Grid operators should streamline the confusing tangle of data center connections applications. The technology sector should maximize the build out of data centers in areas of high power and grid availability, and explore strategies to incentivize their operational flexibility. Better management, policies, etc., of course, matters. Look at another figure. Estimates of the share of the AI in total data center electricity consumption vary widely and are based on are based at best on imperfect proxies for data demands, energy demands. Estimated data center electricity demand due to AI by over 2020 to 2030. So you can see here the US and the world, and there are many models here that we want to bother with, but basically remember that there are large uncertainties in these estimates. Just to look at an example of India, India's total data center capacity and electricity generation mix by over 2020 to 2030 in gigawatts. You can see coal is still there, hydro and wind, of course, natural gas is still there, nuclear and bioenergy. So total installed data center capacity is expected to go more than double by 2030 in terms of gigawatts, and electricity generation mix is going to have still a lot of coal, but it will drop a little, and solar PV and wind will go up. Natural gas is still very much in the mix, and nuclear and bioenergy show up as well, but these are projections, so we have to be careful. Data center total installed capacity in India is set to double by 2030. While coal dominates the electricity mix in India, the share of renewables increases to 35% by then. Is that good news? Well, not good enough, I suppose. Moving on to chapter 3, AI for energy optimization. Applications in today's energy systems. AI for energy optimization, applications in today's energy system. The energy system is complex and evolving. It is becoming increasingly electrified, digitalized, connected and decentralized, with mounting cost pressures. With renewables, solar, wind, it's easy to decentralize the system. These drivers have encouraged energy companies to deploy applications that utilize artificial intelligence to optimize systems, improve production, reduce costs, raise efficiencies, cut emissions and enhance safety. All good things. This chapter provides some details on scenarios and base cases. Oil and gas companies have been among the earliest adopters of new technologies, but they are doing it to boost exploration and production of fossil fuels. We can look at number of supercomputers. Total capacity has grown 70% annually. In the widespread adoption case, AI could reduce costs in the oil field development and operations, potentially improving the affordability of fuels, but it could also have broader ramifications, including increased emissions. So making fossil fuels cheaper is not the best option at this point, considering the emissions issues. AI could also have a major impact on in electricity systems, owing to the complexity of supply, transmission and demand profile. So wide adoption cases mentioned here, and potential cost savings of up to $110 billion annually by 2035 from avoided fuels, and lower costs can be expected in the projections. AI, of course, will enable greater integration of renewable electricity into the grid, which needs to happen because, as we know from the Spain-Portugal case, this is not a trivial issue. Applications of AI in end-use sectors are varied but have significant potential. In the industry, AI is being used to optimize production processes. In the widespread adoption case, energy savings of around 8% could be achieved by 2035 in light industry, such as the manufacturing of electronics and machinery. AI in transport can enhance vehicle operation and management, which could cut energy consumption by up to 20%. It has also applications in reducing contrails and improving electric vehicle ranges. And in buildings, the potential is limited by the rate of digitalization, but there are compelling illustrations of impact, such as on the efficiency and demand response. If you use IoT, automate systems, electricity consumption, water use, at least the wastes should go down. Accurate weather forecasts and analysis of changing weather patterns in a warming world are essential to optimize the operation, planning and resilience of energy systems. AI has been improving the accuracy of weather forecasts and also reducing computational demand. I have podcasts on this already elsewhere that you can look up. The adoption of such AI applications at a sectoral level, sector-wide level, however, is not a given. Various barriers are limiting the extent to which existing AI applications can be implemented, hindering the pace of change. Of course, there are policy issues, data accessibility, interoperability concerns, expertise, digital infrastructure, and so on. Okay. Moving on to, we have 5 chapters, so I will just rattle them off. AI for energy innovation, the potential of AI to accelerate innovation, which is amazing, already happening in every sector, every field. Innovation is essential to achieving secure, affordable, and sustainable energy. Energy sector continues to innovate, and there are some numbers in terms of technology growth, in terms of innovations for oil and gas supplies. Photovoltaic went from 30 terawatt hours of annual generation to around 2,000 terawatts between 2010 and 2024, and electric cars went from 0.01% to over 20% global sales. That's an impressive number, but as long as we are still running fossil fuel cars, this number is not moving fast enough. Innovation takes time, of course, for energy technologies ranging from internal combustion engines and air conditioning to lithium-ion batteries and solar PV. Time for invention to first commercialization averaged over 30 years, and mass market may take up to 20 further years. So we have to always remember that market penetration and socio-technical transitions, acceptances by public, affordability, price range, everything is going to take time. AI is increasingly central to innovation pipelines. In medicine, AI led to a 45,000-fold acceleration in scientific rate of discovery of the three-dimensional structure of the proteins, the functional building blocks of human cells, and now lots of other things in use in surgery, in treatments, telemedicine, and so on. Patent and startup data suggest that AI first approaches to innovation are underrepresented in the energy sector. Only 2.3% of the energy startups have an AI-related value proposition, lower than the 7% for life sciences and 4.3% for agriculture. So looking at sectoral uptake of AI-related values gives us some sense of what the barriers may be and what incentives policies may help change that, if change is a good thing in terms of AI uptake. However, many areas of energy innovation are characterized by the kinds of problems AI is good at solving. Highly complex design spaces, the need to balance performance trade-offs for an optimal outcome, and rich data sets. Okay, so discovery of a perovskite that is stable and easy to manufacture could accelerate cheaper and less space-intensive solar PV. A core challenge of energy innovation is integrating new innovations into complex products and new products A core challenge of energy innovation is integrating new innovations into complex products and new products into industrial scale supply chains. AI can help there in various ways. So AI models can help to detect faults, predict performance, diagnose problems, reducing the risks, costs, and timelines for innovative chemistries, for example, for perovskite. Did I jump it? Yeah, battery gigafactory is what we're talking about. Policy has an important role to play in leveraging AI's potential to accelerate energy innovation. A first step is a more comprehensive inventory of promising technology areas and available AI tools in terms of models and databases. Public policy should support production and dissemination. AI can dramatically accelerate the phase of hypothesis generation. Investment in high throughput or automated laboratories and faster regulatory processes will be needed to ensure testing and certification to keep pace. And there are a lot of people worrying about AI moving too fast. There is the idea that it will get out of control and try to control us, but there is also the idea that we are inserting AI into face recognition, securities, homes, IoT, etc. and there are a lot of security issues to worry about there as well. I think this is the last chapter, but it doesn't matter. Emerging themes on energy and AI, implications for economies, businesses, and people. Artificial intelligence applications address various dimensions of energy security, including adequacy of energy, affordability, system resilience, and the system's ability to emerge from shocks or disruptions. Spain, Portugal example again comes to mind. For example, AI-driven simulations have helped reduce operational costs in various processes. Predictive maintenance is being deployed to reduce infrastructure downtime and improve operational efficiency. Predictive analytics have been helping improve grid stability as well. Simultaneously, the security of energy supply chains is itself critical for the rollout of AI. The electricity system is subject to several critical bottlenecks. These include stretched supply chains for critical components, long lead times of generation and transmission projects, and complex and time-consuming permitting processes. The key consideration is the demand for critical minerals, the supply of which is highly concentrated. For example, in 2030, data center demand for gallium could equal up to 11% of today's supply, and China accounts for 98% of gallium refining. This is a critical issue now coming to rare earth minerals, metals. Every EV cars need lots of these things, and if China, for reasons that are a little obvious now in terms of their battle with the US, if they start hoarding, if they start using militaries to occupy the resources elsewhere, say in Africa, this can get pretty ugly. Data centers are new actors in electricity systems, at least at the scale of the projections being driven by AI development. Okay, the energy industry and technology sector need to deepen dialogue to develop a shared playbook for how to efficiently integrate data centers into electricity grids. This problem is probably being underestimated, since the growth of data centers is super exponential and the grids are not moving as fast. Electricity renewable production in US was taking off, and now policies are hampering them, so we'll have many spin-up cycles again. Cumulative data center investment totals $4.2 trillion out to 2030 in the base case. To cater for data center growth, power sector investment will need to cumulatively reach $480 billion over the next 5 years globally, with nearly half of that taking place in the US. Data center related power sector investment in the US is over 15% of its total power sector capital expenditure in this period. Emerging market and developing economies face several barriers to the scaling up of data center capacity on the one hand, and AI-led solutions in the energy sector on the other. They have to grow energy, they have to grow data centers, they have to match the Nexus, or manage the Nexus as well. By improving expertise is always a big issue. By improving the quality of power supply, fostering local data collection, developing talent, and creating robust policy frameworks, such economies can harness AI to drive more inclusive, future-proof growth. Very nice. Data centers are on track to account for 3% of the power sector and 1% of total energy sector emissions by 2030. 3% of the power sector and 1% of total energy sector. They are among the few sectors that show emissions growth to 2030. Widespread adoption of today's AI applications could lead to emissions savings in other sectors that exceed data center emissions in 2035. However, such AI adoption is not guaranteed and could be negated by rebound effects and increased consumption of fossil fuels induced by AI-enabled lower prices. So if AI is going to be used for enhancing production of natural gas, oil, then they may in fact act against reducing emissions, and maybe some greedy AI operators will begin to use fossil fuels while nobody is looking, or when the regulations are not in place to control energy use by the AI companies themselves, and so on. Okay, so sorry about for being brief, but it's a very nice, very long report and very useful. Lots of nice data, but I got most of the salient points in. That's my judgment. So you definitely want to go back and read the report if you are interested in more details. Okay, see ya.